All right, so welcome to the 13th lecture for STAT 313. Today we'll be studying some maximum likelihood test. We'll be precisely studying 3 tests and doing some example based on that. Okay, so let's get started. So the topic is called maximum likelihood tests. So maximum likelihood tests. So remember what we have done so far. So we have been studying how to compute the maximum likelihood function. And then we found that in the last class, we have seen that we have a beautiful estimate, which is the Rao-Kramer's lower bound for the variance. And then we have seen what an efficient estimator is. Now, today, what we're trying to do is the following. So suppose x1, x2, so we have IIDs, x1, x2, xn, IID with PDF f of x theta. Okay, so where this theta is in the set omega. Now, for the purpose of this section, we'll be considering theta to be a scalar. Later on, we'll be generalizing this to a vector, right? So for example, if we have a normal distribution, remember that theta is actually mu and sigma squared. So here, so that would be a vector, but here we'll be assuming that it's just having one value. So for example, if it's a normal distribution, so suppose sigma squared is known, so we are just trying to compute mu, or the other way around. For example, if mu is known, we are trying to estimate sigma squared. Okay, so that is sigma squared. So that's only for this section. Okay, now we consider the two-sided hypothesis. So two-sided hypothesis. Where my null hypothesis H0 is theta equals to certain value theta sub 0, which is known, versus the alternative hypothesis H1, which is theta is not theta 0. Okay, so where this theta 0 is a specified value. Okay. So that's the setup. Okay. Now recall that how we found the true value of the PDF, true theta value. How do you find it? So found this by using the log likelihood function. So recall that we found using a log likelihood. So the likelihood function, which is given by product of xi theta I from to n. Then we compute eventually the log likelihood function, lowercase l theta, which is the summation I from 1 to n log f of xi, right? And let's consider let theta denote the max likelihood estimate, that is the MLE of theta. So suppose this is a notation. So this is the log, this is a likelihood function. Then we compute the log likelihood function, and suppose this theta hat is the maximum likelihood. Okay. Now let's see. We have seen before that this if the true value is if the true value of theta is theta equals to theta sub 0, if that is a true value, then and if we consider this quantity, say lambda, this capital lambda, which is given by L of theta 0 by some L of theta hat okay. Now we know that asymptotically what we have this quantity, so L of theta 0 is a maximum out of all the L thetas, right? So we have seen before that asymptotically L theta 0 is the max value of L theta we found before. And in fact, we proved this result in the last class. Now, so that means what we have is that, so if we are considering this one, now let's look carefully what this L of theta hat is. So L of theta hat, so theta hat is the maximum likelihood estimator of theta. So by definition, this maximizes the L, right? So L of theta hat is the max. So by definition, you can write by definition of theta hat, L of theta hat is the max out of all L theta. That's how we define theta hat, right? So theta hat is the max likelihood estimate. Okay, so that means its denominator is always more than its numerator. So that means this quantity is less than 1 for sure. Okay, however, if H0 is true, so if the null hypothesis is true, meaning that if we have the true value, if you have the value of theta to be the theta 0, and then what we must have that this lambda, it should be closer to 1, right? Because this quantity should be very close to this one. Yes, so this is the max, but asymptotically again, L theta 0 is the max. So they should match somehow, right? And if they match, so that means this ratio is very close to 1. Okay. So that means if this ratio is not close to 1, then we reject null hypothesis, and we can because then this sentence here and this sentence here will contradict. So this saying that L theta 0 is max, so eventually, so that is a max, but this is the computed max. So they should agree in, if this theta 0 is a true value, they should agree. Okay, so so it should be closer to 1, but if this number is very small, say less than something, then we should reject this null hypothesis, and we can conclude that theta 0 is no longer, or was never a true value, right? So that is the basic idea. So let's write it down in the more formal way. So what we just said is the following. So, let me just write lambda one more time. L theta 0, L theta hat. So theta hat is MLE for, and theta 0 is a true value of theta under H0. These are the two values. So basically, this is the maximum by definition of all computed one, and this one is what we expect to be this maximum. Okay, so note that the first thing is this lambda got to be less than 1 by definition, because this L of theta hat is the maximum, right? However, if H0 is true, then this lambda should be large and close to 1 by the asymptotic analysis, as we have seen. While if L0 L of theta 0 is not the max one, I mean, if it is not, if theta 0 is not really the true parameter, then of course this max. So I mean, if it deviates too much, then if they compute the ratio, that is smaller. While if H1 is true, we'll quantify this pretty soon. Don't worry about this. So this is some just heuristic argument. While if H1 is true, then this lambda should be smaller. That's the way we'll be testing. So here is a for a significance level alpha. Level alpha. So here is the intuitive decision rule. What is the decision rule? That reject H0 in favor of H1 if this lambda value is smaller than some C, where C is such that basically probability of lambda less than C with this null hypothesis, so that is alpha. Okay. So in this case, so this is our intuitive decision rule. So we are rejecting. So this is the decision rule is reject H0 in favor of H1, provided this lambda is less than C. And what is that C? So the probability of lambda less than C under the null hypothesis is alpha. Okay. Okay. So now we call this. So this test is called. This is called the likelihood ratio test, LRT. Okay. Now, later on, we'll be saying something more about this one. We'll be seeing how this behaves asymptotically, this parameter lambda. But we'll come back to this. But first, let's try to understand this. So we'll have some very interesting examples based on this one. So let's start with an example. Now, here is our first example. So this is called the likelihood ratio test for the exponential distribution. Okay. Now, while solving this, I'll have an aside at some point of time, meaning that I'll be showing you some results which are not really directly related to this likelihood ratio test, but it's related to something else. Okay, but I'll mention it when I need it. So what is the deal? So here, suppose that x1, x2, xn are IIT with PDF f of x theta 1 over theta e to the minus x over theta for x bigger than 0, and also we assume that theta is bigger than 0. Okay. So basically, in the language of in the more familiar language, the x follows the exponential 1 over theta distribution. So xi, x1, x2, xn follows x, where x is satisfying some exponential distribution. Okay, so that's a pretty much that's the setup. Okay, now here, what is the likelihood function? So here the likelihood function would function. I'll not do the like I'll not try to find the maximum likelihood estimator because we have done it. If you, I'll refer you back to the one of the first lecture, if not the first lecture, or maybe the second lecture, when we computed the likelihood function or the maximum likelihood estimator for the exponential functions. Okay, but if I write it, the log likelihood function, so it's basically the product of a bunch of this, right? So it's basically product of I from 1 to n f of xi theta. And if I compute this, so it's basically 1 over theta to the n e to the, let's see, it's e to the minus summation I from 1 to n xi over theta. Okay. So again, it depends on how I'm writing this. So I'm just thinking this as a realization, but of course you can write this as capital X as well. Okay. Now you can write this as, so let's write this as with the capital Xi here, so that I can see here, say capital Xi. I'm writing this in terms of the random variable Xi. Now, if I have this, so remember that this quantity, so X bar is really 1 over n summation I from 1 to n xi, right? So summation I from 1 to xi times X bar, so it's really 1 over theta to n e to the minus nx bar over theta. So that's the likelihood function. Okay. We have computed the max likelihood estimator before. We found, again, I'm referring to the second lecture. Okay. So this is from the second lecture, so lecture 2. So this is what we did. So here we have the x1, x2, we computed this one, and we finally found that this is the maximum likelihood estimator. Okay. So this is in lecture 2. Okay. Now we found that the maximum likelihood estimator in this case was x bar is the MLE of theta. Okay. So once again, I refer you back to the lecture 2. Okay, so now, therefore, let's compute, therefore, up to this is, let's call this the finding the likelihood function and then simplifying this. Now what I'm trying to do, therefore, for the likelihood ratio test that we developed, let's compute that lambda, which is equal to L of theta 0 over L of theta hat, which is the estimator. And what is that? That's x bar, right? So which is L of theta 0 over L of x bar, because we have found that this is x bar, right? So what would be that? I can see that we have basically, so L of theta 0 would be 1 over theta 0 to the n e of minus nx bar over theta 0 over L of x bar would be 1 of over x bar to the nth power e of minus n, right? X bar over x bar cancels. So what we have is, therefore, lambda is this e to the n goes to the top. So it becomes e to the n. Now we have x bar over theta 0 to the nth power and then e to the this quantity, right? Minus nx bar over theta 0. So that's my lambda. Let's box it. This is the lambda for the likelihood ratio test. Okay. Now, what was the decision rule? Let me just show you the decision rule one more time. So this was the decision rule. So the decision rule is if this is smaller than a number, a particular number, so then we reject the H0 in favor of H1. So that is a goal. So similarly, in this case, we can say, hence, the decision rule gives us that we can reject H0 in favor of H1 if, so this lambda is then C. Okay. Now we'll try to further understand this. Okay. So we'll try to further understand this for this context. Okay. So more details about this decision rule of this. Okay. Now let's see what we're trying. So this lambda up this constant. So remember, just write lambda again. Lambda is to the x bar over theta 0 to the n, and then e to the minus 1 nx bar over theta 0. So that's lambda, right? Now this is a constant. E is a constant and n is a number which is given. So this is a constant. So then this constant, so this basically, if I can write this one as say g of x bar, right? Where g of x bar is really this quantity, right? X bar 0 to n e n x bar theta 0. So lambda as e to the n times g x bar, where g of x bar is. Now I want to keep repeating this x bar again and again. So that is, I'm writing a function g of t, which is really this t to the I can think function of x bar over theta 0. Right? So I can write this as x bar over theta 0. G of t is t to the n e to the minus nt. T is bigger than 0 because x bar is bigger than 0 and theta 0 is bigger than 0. Let's count this function. So what we are having here really is so this is I'm writing this theta bar. So this I'm just adding this x bar over theta 0 for the convenience of location for the convenience of notation. Because now I can just write this way. Okay. So let's figure how this function behaves. Where this t is okay. So you can write, so the test statistic, lambda looks like is in the form x form except for the constant e to the n, which is a constant. Gt equals e to the r t to the n e to the minus nt, where this t is really x bar over theta 0. Why? Because remember that the way we obtain it from here, so this is the sample, this is the sample mean, so its realization is little x bar and theta 0 is theta 0. Okay. Okay. Now this is a very interesting function. If you plot this, it looks like this. So this is GT, this is T. Okay. How do you check it, or how do you check this plot? I mean, observe that I'm writing it in the bracket because you can just plot it. Observe that G prime, let's differentiate this with respect to T. So G prime T is nt to the n minus 1 e to the minus nt minus n e to the minus nt t to the n. That's my G prime of T. And G double prime of T after this one is going to be n times n minus 1 t to the n minus 2 e to the minus nt. I'm differentiating the first one minus n squared t to the n minus 1 e to the minus nt. If I differentiate the second term, and this one is going to be minus n squared e to the minus nt t to the n. And finally, if I differentiate this one, so it's minus n times so here actually this is plus because there is a negative sign up front anyway. So if I differentiate the n thing, it's minus, and then this is going to be n times n minus 1 e to the minus nt t to the n minus 1. Yeah, this looks more or less correct. Okay, so now observe that this quantity G prime T is 0. G prime T is 0 gives you the fact that basically T to the n minus 1 equals to T to the n, which implies T is 1. Okay. And at the point T equals to 1, G double prime of 1, so that means the second derivative, if I just plug in T equals to 1, it becomes n minus 1 e to the minus n squared e to the minus n plus n squared e to the minus n minus n minus 1 e to the minus n. Sorry, I made a little mistake here. So this term should not be n minus 1. So this is n squared here. So this is going to be because when you're differentiating this to the n, it's n times, and there is an n. So what I have here is it doesn't change anything. So only my last term comes n squared here. Okay. Now look at this term. So it's basically, I mean, this and this cancels. And I have n squared to minus n minus e to the minus n e to the minus n minus squared e to the minus n. So it's minus n e to the minus n, which is negative. So that is at the point t equals to 1. So t equals to 1 provides a max. This is just an aside, it's a calculus exercise. So that means this point is t equals to 1. Right? So now, remember that if this quantity is small, I mean, whatever small we want it to make. So suppose we make our decision rule that, I mean, suppose we have, we'll be rejecting the null hypothesis provided this value here is more than C2 or less than C1 because it's max here. So this the statistic, so its value, if it's less than C2 or more than C1, will be rejecting the null. Sorry, less than C1 or more than C2 will be rejecting the null hypothesis. So let's do this way. So hence, we reject H0, that is less than C, lambda less than C, if and only if, say, we are in this particular region, so which is T is less than, and T is what? So it's basically, so remember that T was constructed out of X bar over theta 0, right? So this quantity, that means I need X bar over theta 0 is less than C1, or X bar over theta 0 is more than C2. So in that case, will be rejecting the null hypothesis. Now, you may wonder that why I even did not consider, I mean, where did it come from? So basically, I mean, you can just, you're welcome to use this one as a whole. So, I mean, this, the problem is this e to the n is a constant, right? So this constant, so let me just write this way. So basically, this quantity, what you have here is a constant. So uh, what we are saying is, other than this constant, this is what I showed the graph of. So it's basically going up and down. It has a certain maximum at x bar over theta 0 equals to 1, right? So that means when this quantity is small, then this lambda is small. When this is very big, this lambda is big. So that's the deal. So ignore this constant, because that e to the n is included in that constant. So what we were trying to construct. Okay. So even this relation is true without that. Remember that what I wrote, like lambda less than c. So I can divide this c by e to the n. It's still a c, right? So I'm really focusing on this one when this quantity is small. Okay. So, note that lambda over e to the n, which is less than, in this case, c over e to the n. Let's call this another constant c. Rename. So that means we are really concerning with g of x bar over theta 0 less than c. So that's why we are just focusing on this function. If you wonder why this constant is not in play, because this is always the case. Whenever there is a constant, we just disregard it. Okay, now with this, now we are ready to, so this is our working hypothesis. So this is our decision rule. Okay, but still we don't know how it looks like. Okay, so what would be our confidence interval? What would be our other things? So all we know is basically GT function looks like this. So this is my g of x0 over theta 0. And here it's my x bar over theta 0. This is the point 1 max. And we are saying that when it's more than C2, we'll be rejecting, or if it's less than C1, we'll be rejecting. It's a two-sided hypothesis, right? So I mean, we'll be just, we're trying to conclude that x bar is, I mean, this theta 0 is a actual estimator of the true value. Okay. Okay. Now, how do you understand a distribution of this quantity? So how do you understand a distribution of this thing? Apparently, we don't know yet. Okay, so here I need an aside to understand the distribution of x bar over theta 0. That is our goal now. Okay. So that would need me an aside. It's a very important aside. Okay, it goes like this. So if we have so the result we are trying to prove is the following. I'll write this in 3 steps. One is, note that if I have bunch of IIDs, x1 follows a gamma distribution alpha 1 beta, x2 follows gamma of alpha 2 beta, xn follows gamma of alpha n beta. Remember, so the gamma has two parameters, alpha and beta. So I'm keeping the betas to be fixed. I'm just varying the alpha. So then it an xr1, x2, xn are independent, though not identical distributed here. The distributions are different. So then a general result shows me I from 1 to n xi. It follows a gamma distribution with summation I from 1 to n alpha I and beta. In particular, if there are IID, so the first quantity is n alpha. That's my first result I want to mention. Now, what is the special case of this one? Special case. We know that if x1 follows exponential distribution with parameter 1 over theta 0, like we have in this problem, x2 follows exponential with 1 over theta 0, and so on. So this is same as gamma of 1 comma 1 over theta 0. So this is exponential distribution means gamma first parameter is 1. So that means summation I from 1 to n xi, in this case their IID, it follows the gamma of there are n quantities and 1 over theta 0, right? Why 1 over theta 0? Because look at this thing, beta does not change. Okay. So the second parameter is always the beta. Okay. I'm just writing n of those here. Okay. This is my first observation. Second observation. It goes like this. If y satisfies gamma of alpha beta, and then it has a scaling property, then cy follows gamma of alpha beta over c. Okay. It's the second result. What I wrote here is the first result. Result 1 is this one, result 2 is this one. Third result, and in the final one, why I'm doing all this. It's known that it is known that if I'm trying to think about letters, say k satisfies gamma of little k over 2. That's why k is a bad notation. Say j. J satisfies gamma of k over 2, comma 1/2. Then j satisfies chi-square distribution with k. Okay. Now let's see based on this one. Now summation I from 1 to n xi for x1, x2, xn IID with exponential 1 over theta 0 under h0, right? Because under h0 their theta is theta 0, right? So under h0 because I'm using theta 0. So this satisfies gamma of n theta 0 by 1 to some extent. Right here I wrote it. That means if I multiply both sides by say 2 over theta 0, summation I from 1 to n xi, this is my constant c. So this follows gamma of n comma beta over c. So it's already 1 over theta 0 over 2. right? So which is gamma of n 1/2 by 2. So that means by 3, this quantity 2 over theta 0, I from 1 to n, xi. What is gamma of n or n comma 1/2? If it's k over 2 comma 1/2, it's same as chi square k. So if it's n comma 1/2, it's gamma. It follows chi square of 2n. So this quantity satisfies chi squared of 2n distribution, provided xi's are independent IID following exponential distributions, right? My aside is done. So this is the end of the aside. End of aside, which I started right here. Okay. So here's aside, and here is the end of aside. So we found that this quantity follows chi square. Now let's get back to the original problem. So now we have we know that what is, by the way, what is x bar? So this is really speaking. So we have to basically find something in this way, right? So now, how do you understand this? So, well, this is nothing but basically it's a version of summation of xi's, right? So let's see. So we can simply write that we observe that this 2 over theta 0 summation I from 1 to n xi follows a chi-square to n distribution. We have just checked, just shown in aside. Okay. So hence, we can reject, and the quantity that we are testing is very similar. So note that so x bar is what? It's 1 over n. So this is really meaning if I multiply by that n, so it's really 2 over theta 0 summation I from 1 to n xi less than nc1 to nc1, right? Or 2 over theta 0 summation I from 1 to n xi is bigger than 2nc2. So these are the two conditions. I didn't write before because in that case it would mean, you may wonder why I get this quantity 2nc1 or 2nc2. But here is an explanation of why that quantity is useful. Okay. So therefore, we can reject this, and now we understand how this behaves, right? So we are trying to really understand this quantity 2 theta 0 summation I from 1 to n xi. And we have seen how it behaves. It follows chi-square. So we can reject it if it's too small or too large. Right? So reject h0 in favor of h1 if 2 over theta 0 summation I from 1 to n xi, it's less than, so suppose we are setting up the alpha level test. say chi-squared of 1 minus alpha over 2 to n, or is 2 over theta 0 I from 1 to n xi is bigger than chi-squared alpha over 2 to n. Okay. So these are the these are the quantities that we are computing based on the chi-square equivalence. So we have this one or this one, right? Once again, remember that for chi-squared, so we have something like this one. So if your significance level is alpha, alpha level test. Significance levels is alpha, meaning that if we are having, I say maybe this region is alpha over 2, and this region is alpha over 2. So basically, so this is the chi. So I mean, the chi-squared of 1 minus alpha over 2 would be somewhere right here. So chi-squared of 1 minus alpha over 2 means this region, and so this is the value of, this is also alpha over 2, and we are talking about this one as chi-squared of alpha over 2, and this is chi-squared of 1 minus alpha over 2 because the region to the right of this one is 1 minus alpha over 2, right? So we're talking about the region to the right. Okay. That's it. So now, of course, I mean, this is not the only choice. Of course, if you don't like this method, I can change everything here. I mean, maybe you can just stick to the C1 and maybe work with that one. But this is a good relation between this chi-squared and this exponential distribution that we derived. Okay. All right. So once again, if you have any question, you're welcome to send me email. This is a little difficult stuff, so please follow this carefully. And we have done a lot of different things here. Okay, let's see. Let's do one more, say likelihood test. So here's an example. This is called the likelihood test, likelihood ratio test for mean of normal PDF. Remember, in this section, our theta is scalar, so we cannot estimate both at the same time. But suppose we know sigma squared. How do you expect? How do you compute the mean? It's easy. So consider that x1, x2, xn. So this is a random sample from a normal theta sigma square distribution, where the value of theta is unknown and sigma squared is a positive number is known. So the only unknown quantity is this theta. So the mean is unknown. So let's consider the hypothesis. So hypothesis is H0 is theta is some certain value theta 0, which is specified, versus H1 is theta is not equals to theta 0. So that's our standard hypothesis testing. Okay. Now let's compute the log likelihood function. So in this case, the log likelihood function, or the likelihood function, sorry. So likelihood function will not compute everything in details because we have already We have already discussed this in details before. So how do you compute the likelihood function? So L theta, I'll just write it down because if I want to compute everything, it may take longer. So it's 1 over 2 pi sigma squared to the n over 2, and then e to the power of minus 1 over 2 sigma squared, and then summation I from 1 to n xi minus theta squared, which can further be written as 1 over 2 pi sigma squared n over 2 e to the power, let's first write 1 over 2 sigma squared summation I from 1 to n. Remember that for the case of normal distribution, we've seen that the maximum likelihood estimator for theta is x bar. So let's write this in terms of x bar. So let's write it's xi minus x bar squared, and then we write e to the power of, I'll try to compensate that by 1 over 2 sigma squared, and then we write n x bar minus theta squared. You can check. It's basically the same expression. Okay. So all we did is we are here, it was theta squared, and we make it x bar squared, and this is the compensator, whatever you need to. By the way, here is a negative sign. So here is a negative sign. Let me just write it here. So it's basically exp minus 1 over 2 sigma squared n x bar minus theta squared. So that is the quantity. Okay. Now the maximum likelihood estimator of theta is theta hat, which is x bar. We have done this before. I'll not repeat it. So the quantity lambda, which is L of theta 0 over L of theta hat. Okay. Which is given by, let's see, so L of theta 0 is basically the same thing with wherever I see theta, I replace by theta 0. So that means the only place in this expression, it will be x minus theta 0 squared. And then the x bar, so this is going to be L of x bar, right? Now, well, L of x bar will of course be, so this will go away. So for the denominator, for the numerator only it will survive, right? So basically, what I will have is the following. If I compute this quotient will be gone. This quantity is independent of theta, so it will be gone. So I'll have e to the power of minus 1 over 2 sigma squared n. I'll have x bar minus theta 0 squared. And for the denominator, I'll have for theta hat, which is 1 e to the power of minus 1 over 2 sigma squared n of x bar minus x bar squared, which is e to the. Okay. So this is basically just a numerator. So this is 1. So it's e to the power of minus 1 over 2 sigma squared n x bar minus theta 0 squared. So that is my lambda. Okay. Now, what does it mean to have these quantities? Then the log, then the likelihood ratio test, which we called LRT, gives me that we'll reject the null hypothesis if lambda is less than c. Okay. We reject H0 intuitively, and therefore now this really means that we'll reject H0 provided log of lambda is bigger than log of c, because log is an increasing function. And that means if I multiply this, you'll see why. If I multiply this by minus 2, this is true. Log c. Okay. Now let's plug in the value of this lambda, and you will see that minus 2 log of that quantity is minus 1 over 2 sigma squared n x bar minus theta 0 squared, bigger than minus 2 log c for our case. Okay. So which is really, so this minus minus cancels, this 2 and 2 cancels. So what I'm really having is, if you look at this carefully, it's x bar minus theta 0, and I can write there's an n here, so it's sigma over square root of n, right? And then the whole thing squared is bigger than minus 2 log c. Okay, but we have seen before that this, so x bar is the sample mean under H0. E of x bar is theta 0, and variance of x bar is always, okay, under H0 is this one. So this is sigma squared over n. It's always. But under H0 is this one. Okay. So that means this quantity is really, so under H0, this x bar minus theta 0 over sigma square root of n, it follows a standard normal distribution. So that means it's squared follows a chi-square distribution. Okay. So that means the test that we developed right here, we are basically saying that a chi-squared value is bigger than minus 2 log c. So if we have, if we have the value of this chi-squared bigger than certain thing, then we declare we reject the null hypothesis. So let's write now the conclusion. So the likelihood ratio test with significance level alpha states that we reject H0 and accept H1 when this quantity minus 2 log of lambda, which is equal to, so this quantity is minus 2 log lambda, right? So that's what we derive, which is equal to x bar minus theta 0 over sigma over square root of n squared is bigger than chi squared 1. Okay. So that is the it's the same as a z-test for the normal mean, right? Where only that S is replaced by sigma. Okay, so this is how we can use the log likelihood test, or sorry, likelihood ratio test for the mean. Now, I'll write one more result, and after that, I'll solve some of the other problems. So this is based on all this. So there is a very powerful result. You see this quantity, this -2 log of lambda, and in this case, it is something like this one. It has a special significance. So in this case, it's already a chi-squared. But in many other cases, if the original distribution is not a normal, then there is no reason why this should be a chi-square distribution. So what will happen in that case? And that is, I'll not prove the theorem, but I'll just write this theorem. So under some regularity conditions, I'll not discuss this. It's very similar to as we wrote those R0 to R4 and then something else also. Suppose assume that some regulatory conditions are true. I'm making it very vague in the sense that what is some? It's basically the previous ones and some more, but I'll not mention it. Then under the null hypothesis, H0, which is theta equals to theta 0, under this null hypothesis, this quantity -2 log of lambda that we computed, it's actually converging distribution to chi-squared 1. It's true irrespective of any original distribution. Okay, so I mean, we have seen that this is true for the normal case anyway, but even when the original the starting distribution is normal, not normal, it's still true. Okay, now let's solve one of the example problems. So let's start with say this one. So here is an example. So this is exercise 6.3.1. It goes like this. Test. Well, so the following data are generated from an exponential distribution with PDF f of x theta, which is 1 over theta, e to the minus x over theta for x bigger than 0, where theta is 40. Okay. And the data are 19, 15, 76, 23, 24, 66, 27, 12, 25, 7, 6, 16, 51, 26, 39. So this is the data. Fairly small data. Okay. Test the null hypothesis theta equals to 50 versus H1 is theta is not equal to 50. determine the decision at level alpha equals to 0.10. Okay. All right. So again, since somebody provided us that this information, so this is given, and we are trying to test it, so we almost know the answer, right? So we should get that we should reject the null hypothesis and we'll accept the alternative hypothesis, but that is only because this is given. Okay. Usually this part is not provided. Usually you just see the data, so there is no way you have any information about that. So, but here we sort of know the answer. Okay. So here is a solution. Let's just solve it. So solution. Well, we have already constructed the test statistics. So 2 over theta 0 summation I from 1 to how many data are there? So we have, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 data and then xi, right? So which is really speaking, in our case, it's 2 over theta 0 is given to be 50. And if you add everything, you'll get 432. So this is 17.28. Okay. Now, our significance level is given to be, so alpha is given to be 0.10, right? So therefore, if we are seeing the previous test, which is, let me just, so here is what we have for the test. So it's less than chi-squared this quantity. So it's basically the 30 degrees of freedom. And so we need, so alpha is 0.1. So we need to compute the value of chi-squared alpha is 0.5. So that means alpha is 0.1. So this is really 0.05 and 2n is 30. So that is one quantity we need to find. And the other one we have to find chi-squared of 0.95 and 30. Now from the table, you can check that this one is going to be 43.77 and this is going to be 18.49. Okay. So therefore, so what do you need? So we need this quantity to be smaller than the 1 minus alpha over 2. So this is really chi-squared 1 minus alpha over 2 2n. And this is really chi-squared alpha over 2 2n. So it is, so let's write this number. So first one is 17.28. Is this true that this is less than equal to 43? .77? Yes. Okay. And hence, so that means this quantity, which is this one, is less than this one. And hence, one of these conditions is satisfied, right? The first one. And therefore, we reject null hypothesis. So we conclude that we reject H0, which is theta equals to 50, which is sort of expected. It is expected as the data is generated from theta equals to 40. It's given. So this method is even more powerful when we don't know that information, but still we want to conclude something. So then the real power of this method. Okay, let's do one more, which is So let's compute, say, 6.3.9. So this is example from the exercise 6.3.9. Okay. So this goes like this. Let x1, x2, xn be a random sample from a Poisson distribution with mean theta. Okay. The first part is suppose all right. The first part is show that the likelihood ratio test of H0, which is theta equals to theta 0, versus theta versus the alternative hypothesis, theta is not equal to theta 0, is based upon the statistic. Y, which is I from 1 to n xi. And then I'll be writing, so obtain the null distribution obtain the null distribution of y. So that's my first part. And the second part is for theta equals to 2, theta 0 equals to 2, n equals to 5, find the significance level of test that rejects H0 if y is less than 4 or y is more than 17. So let's do this. So let's solve this. So solution. So let's see. So what we are trying to do here is we are trying to, first of all, we are the first part is asking us to create a rejection rule based on this one. Now we have already seen that the maximum likelihood estimator of theta is given by x bar for the Poisson process or the Poisson distribution. So we have seen before the MLE of theta is theta of hat is x bar for Poisson distribution. We have seen it, right? And therefore, lambda, which is given by L of theta 0 over L of theta hat, which is same as L of, by the way, also we also computed the log likelihood functions before, right? So L of theta for the Poisson case, it's basically e to the minus summation xi, I from 1 to n. I'm interchangeably using little x on big X. So when, I mean, it's really, I mean, whenever I'm thinking of a sample which is given, I'm using little x. Whenever I'm thinking this is a random variable, I'm using a big X. Okay? So this is the quantity. So e to the minus lambda um, e to the minus, sorry, let me just write this way. So it's e to the minus n theta, and then theta to the um, x, which is in this case summation xi, I from 1 to n, over x1 factorial, x2 factorial, xn factorial. So this check, we have done this before. It's very easy to derive. Okay. So now in our case, we are trying to compute L of theta 0 over L of, so this is really x bar, right? Let's see. Once again, as I'm saying that I'm interchangeably using upper case and lower case. So whenever I'm thinking of a sample, I'm using lowercase. Whenever there is no sample, I'm using uppercase, right? So let's write this. So what is this quantity? So this quantity is e to the minus n theta 0. And then we have theta 0 to the summation xi, I from 1 to n, over this one. And this one is same for numerator and denominator because this is independent of theta, right? So this will cancel out. And for the denominator, I have to replace x bar by theta, theta by x bar. So I have to write this as e to the minus n x bar times x bar to the summation I from 1 to n xi. Okay? It's messy, but it is what it is. Okay. Now you can simplify this in the following way. You can write this in the following. Let's see. Whenever you have this nx bar, so this is really, so nx bar is really summation I from 1 to n xi, isn't it? So this quantity nx bar, I can write that in terms of summation. Okay. So let's write this. It's e to the minus n theta 0, summation I from 1 to n xi. And then this is e to the minus summation I from 1 to n xi. And this is summation I from 1 to n xi over n to the summation I from 1 to n xi. A lot of notations. Okay, but that's it. Okay. Now let's try to understand this quantity. So this quantity, I can see that it has e to the minus n theta 0, which is a constant. So it's basically e to the minus n theta 0, which is a constant, times, here, can I write the following? And now follow this carefully. So I can write this as theta 0 to the y e to the minus y, and this is y over n to the y, where y is summation I from 1 to n xi. I use this notation. So it's constant times this one. So let's massage this a little bit. So it's basically a constant c times, so it's e to the y, and the rest would be, let's see, can I write this as y, and then this n and theta 0 together, n theta 0 to the minus y. So lambda is really a constant times e to the y, y over n theta 0 minus y. So that's the lambda, right?
Once again, as we have done the tests before, let me just show you one more time. This is something will encounter again and again. Whenever there is a constant, we'll tend to ignore it and we'll be using whatever is there other than the constant. So let's see it here. So whenever we have a constant, look at one of the previous examples that we did. Here, this lambda less than c is same as if I divide that lambda by constant and then work with that. So I'll be using the same procedure. So we reject h0 if lambda less than some c. Okay, so now this is also c. So let's just to distinguish these two. So let's write here c0. Okay, c0 is nothing but that constant. So that means I really have c0 e to the y over n theta 0 minus y is less than c. So that means I really have e to the y. It's sufficient to consider the constant c, okay, where c is c over c0, a constant. Okay. So whenever this is sufficiently small than a particular constant, and we'll determine what constant we are talking about very soon, but that is the thing. Now, we can say that, okay, so let's now talk about this constant. So let's consider a function, say, so let's try to plot this one. So fy equals to e to the y n theta 0 minus y, okay? So I'll leave it up to you. Just find that, if you want to differentiate this, you can take a log of fy. So it's going to be y minus, let me just do one part and then I'll leave the rest. Log of y minus log of n theta 0, and then differentiate this. So you get f prime y over fy, which is equal to, you can check, it's going to be minus log of y over n theta 0. So if prime y equals to 0 really means y equals to n theta 0 from here. It's a calculus computation. Okay. Also, let's compute the second derivative. So you can check that the second derivative in this case, so also f prime is really f times minus f times log of y n theta 0. So compute f double prime from here. So it's going to be minus f prime. I'm just dropping all the suffix. Log of y over n theta 0 and minus f. And if you differentiate this log function, it's going to be n theta 0 over y over n theta 0, right? So at the point y equals to n theta 0, f prime is 0. So f double prime is going to be, so this is 0. And then this one is going to be, if you compute, minus f, which is a positive number. And then y is n theta 0. So it's 1 over, so it's 1 over n theta 0. Okay. Now, f is a positive number. This is a positive number. So this is a negative number. So y equals to n theta 0 is a max for fy. It's just a calculus. Okay, so it's a calculus exercise. So we found a maximum for this function fy, and that is at n theta 0. So we can say that, we can think about this function. It has just a one max, and I can think this function as something like this. So it's going somewhere at the max, and the max is n theta 0 with respect to y, where this is fy. So I can accordingly build the critical region. The critical region can be obtained as bigger than or less than some particular number. Let's write the next page. So So we reject H0 if Y, and what is Y? So Y is really, we wrote this Y somewhere. So what is the Y that we defined? So we defined this Y as summation of Xi, right? So this is basically Nx bar, Nx bar, because summation of so X bar is summation of Xi over N, and this N cancels. So this will reject this if Y is less than C1 or Y is bigger than C2. So that's it. That's it for part A. Part B, so that is our decision rule. So whenever this Y is some constant and some other constant, then we reject the null hypothesis. We'll not specify it here. So if I draw a picture, so if we have this Y, so maybe this is the Y random variable, and maybe when it's more than C2, we reject it. When it's less than C1, we reject it. Okay, that's the rejection region. Part B was, let me remind you what part B was. It's given that theta 0 is 2 and n equals to 5. We have to find the significance level of the test to reject H0. Okay. So basically, under H0, Y follows a Poisson distribution with the parameters basically. So what is the parameter? So it's n times theta 0, right? So that's a parameter for the Poisson distribution. So what we are basically, why we're using is because Xi's are Poisson with parameter theta 0. And then x1 plus x2 plus xn, that is my y. So there are sum of IID. So it will be a Poisson with parameter theta 0 plus theta 0 plus theta 0. So which is Poisson n theta 0. So that's what we are using. Okay. The sum of independent Poissons are Poisson. So under null hypothesis, that's the case. So what is the alpha? Alpha is under the null hypothesis. We want y is less than 4 and y is more than 17. So this is under theta 0 equals to 2. That's the null hypothesis, right? Now, in this case, so we have what is the n? So n is 5 and theta 0 is 2. So n theta 0 is 10. So that means your y is really a Poisson 10 under the null hypothesis. Right, now it's very easy to compute this number. So basically you compute the probability that the Poisson distribution with parameter 10 is less than 4, equal to 4, and it's more than 17. I'll leave it to you to compute this. So the first number should be around 0.293. That's 0.0270. So if you add this to it's 0.563. So that's answer. Okay. It's assuming that you're using the independent Poisson, and then the sum is Poisson. Okay, now we are almost done. So the based on this all the tests, we can even derive further tests. So let me just mention this. Some additional tests. So what we did so far, we studied the likelihood ratio test. Two other tests. I'll just mention it. The first one is called the Wald type test, named after Wald, Abraham Wald, which goes like this. So what we do is, here the null hypothesis and the alternative hypothesis are as before. So H0 is theta equals to theta 0 versus H1, which is theta is not equal to theta 0. Okay. So what is the Wald type test? So here, step 1, you construct a test statistic. I'll not discuss this in details, but consider the statistic, which is given by chi squared w, which is square root of n I theta hat. Again, this is the Fisher information that we discussed in last section, theta hat minus theta squared. Okay, step 2, reject H0 in favor of H1 if chi squared w, this quantity, is more than chi squared 1 with alpha. So it's a significance level alpha. Okay, so this is one of the, it has asymptotic level of significance alpha. I'll not elaborate on this one. So this is my, if I call this one number 1, this is number 2. And then the third test, third and last test, it's called Rao's score test. And this Rao is after the famous C.R. Rao. Okay. It goes like this. So step 1. So here the statistic you consider chi squared r, which is given by the first derivative of the log likelihood function and divide by square root of n I theta 0 and squared. Note that for while for the Wald test you need theta hat, here for Rao's test you don't even need any theta hat, right? And step 2, you decide that reject H0 in favor of H1 if chi squared r, so this statistic value is more than chi squared. So this is the same as the Wald test. So these are the two other tests which can be useful in practice. Okay. Now, I'm thinking that we should do at least one example which illustrates these things. So let's try say one of the problems, and that's it. So here is an example, and this is the exercise 6.3.16. Okay, so let's discuss this one. So it goes like this. So let x1, x2, xn be a random sample from a distribution with the probability mass function p of x theta, where theta is unknown, is theta to the x 1 minus theta to the 1 minus x, for x can be 0 or 1, where is 0 less than theta less than 1. We wish to test h0, which is theta equals to 1/3, versus h1, which is theta is not equal to 1/3. So that is the setup of the test. There are three parts of the problem. First part, find lambda and -2 log of lambda. Let's do step by step. Okay. Now here's the solution for the first one. In this case, the L of theta, we have done it before. This is nothing but theta to the summation of xi, 1 minus theta to the n minus summation xi. I can write this in another way. I can write this theta to the nx bar, 1 minus theta to the n minus nx bar, because x bar equals to 1 over n summation xi. Okay. So therefore, my L theta would be log of L theta, which is basically nx bar log of theta plus n minus nx bar log of 1 minus theta. So that is L theta. Okay. Also, I mean, I'll not show it. We have done this before. We have found before that in this case, the Fisher information so Fisher information I theta, we have found this before, so I'll not do it. Actually, we have done it last class. See last class. Okay. So this is my I theta. Okay. Now, so let's find lambda. So what is lambda? So lambda is, I'll not need I theta for part A, but I just wrote it for convenience. So what is this quantity, lambda? So this is really L of theta 0 over L of theta hat, right? By the way, what is the estimator? So this is the MLE of theta is theta hat. We have done this many, many times. It's x bar. Right? For this case, so the x bar is the MLE for theta. So this is going to be, if I compute this L of theta 0, so which is really theta 0 to the power of nx bar, 1 minus theta 0 to the n minus nx bar over theta hat is x bar. So it's x bar to the nx bar, and then 1 minus x bar to the n minus nx bar. So let's follow this up. We are done actually. So what is theta 0? Theta is 1/3. So if I write this, it's basically 1 over 3x bar to the nx bar if I combine these two terms with theta 0 equals to 1/3, and this is 2/3. So it's 2/3 over 1 minus x bar to the power of n minus nx bar. That's it. So this is the answer. So this is what that lambda is. So lambda equals to this. Okay. So this part, I mean, we can even compute. So now what is minus 2 log lambda? So minus 2 log lambda from here is very easy. So minus 2 log of lambda is basically minus 2. If I take the logarithm of this thing, it's nx bar log of 1 over 3x bar plus n minus nx bar log of 2 over 3, 1 minus x bar. That's the answer. And why this quantity is useful? You have seen that this quantity is, I mean, approximately when we wrote the asymptotic result that note we have seen that this minus 2 log of lambda, it goes in distribution to chi-squared of 1. And that's why we sometime consider this quantity. Okay, but that's part A. Now, part B. It tells you to determine the Wald type test. Okay. Solution. In this case, Wald type test statistic is given by what? So it's let me just show you right here. We have the information we already computed. Theta hat is x bar. So it's essentially square root of n I x bar minus theta squared, right? And under the null hypothesis, we are trying to test this. So under the null hypothesis, H0 W squared is given by, essentially it is, we found Ix to be, so it's square root of n 1 over x bar 1 minus x bar. So that is this quantity. And then we have x bar minus, so the null hypothesis is 1/3. So this squared. So essentially, I can write this in a little better form. I can write this x bar minus 1/3. And then suppose I write this way, x bar 1 minus x bar over n squared. So that is the Wald type test statistic. Okay. And finally, part C is what is Rao's score statistic? So in this case, we have already seen what is L prime of theta 0. So we have already computed L prime of theta, which is right here. So note that I have already computed L theta. So if I differentiate that, I can compute L prime of theta. So let's see. L prime of theta 0, so here's the solution, is so basically if I differentiate that with respect to theta 0, so it's nx bar over theta 0 plus n minus nx bar, it's minus 1 minus theta 0. So that is the quantity. In other words, I can compute this as theta 0, 1 minus theta 0. So this is nx bar minus nx bar theta 0 minus n theta 0 plus nx bar theta 0. So what we ended up with is really nx bar minus theta 0 over theta 0, 1 minus theta 0. So that is the L prime of theta 0 in the quantity, and then rest are known. Hence, so chi squared r is really equal to n x bar minus theta 0, theta 0, 1 minus theta 0. And then we write this 1 over square root of n. So we have done this before. So it's basically square root of n theta 0, 1 minus theta 0 from the last one squared. So this is, I can write this if I, after some simplification, actually, let's see, did I write it correct? Probably not. So let's write it again. Chi squared r is L prime. We have just computed. It's nx bar, sorry, nx bar minus theta 0 over theta 0, 1 minus theta 0, and divided by n of theta 0, 1 minus theta 0. Yeah, it's divided by squared. And if you simplify this, it's square root of n x bar minus theta 0, square root of theta 0, 1 minus theta 0, and then whole thing squared. So this is the Rao's test statistic. All right, so so these are various ways of computing it. I think I made a small error, and so for wall type test, so please make this correction. So when I write this wall type test, so there was a theta 0 here. Okay, so yeah, for respect to, so there was a 0 here, and consequently when I write this one, so there should be a 0. So basically I don't even have to write under null hypothesis. So now theta 0 is 1/3. So now I can simply write 1/3 wherever I see theta 0. So it's n x bar minus 1/3, and this is 1/3, 2/3 squared. So this is really speaking 2 over 9. So it's 9 over 2, and then x bar minus 1/3 squared. So this is the Rao test statistic. Okay. All right. So we understood various tests today. So these are really, really important. So we studied all these tests. We have primarily studied 3 tests, Wald, Rao, and the maximum likelihood ratio test. So next class, we'll be starting a new chapter. Okay. Thank you very much.